Ladies and gentlemen, it is a pleasure to welcome you to this presentation on frequency modulated continuous wave analysis of dynamic load deformation in geomaterials. I'm Jamie Blanche, the lead researcher, corresponding author and presenter of this novel research at this virtual OTC event. I certainly hope this recorded presentation will give clarity and insight into this truly unique application of microwave sensing. I represent two organizations on this occasion, both based at Eric University. The Orca Hub, the offshore robotics certification of assets, a research hub for integration of robotics into the offshore environment and the application of novel sensing methods. I'm also representing the Smart Systems Group at Heriot-Watt University, where our core mission statement is to transform data into actionable information. So to give a brief overview of today's presentation, we'll start with an outline of the technical challenge. We'll go into the applications to date. We'll touch on some of the theory of deformation and failure mechanisms. I'll go into some of the equipment characterization, so the antenna, the electronics, and the samples themselves. We'll talk about the experimental setup. We'll go into the results of the experiment. Then we'll discuss and conclude what those results appear to have been. And given that this isn't a live presentation, I'll be unable to take questions, obviously. But I've certainly given my details so that you can correspond and ask any questions offline, which I'll be more than happy to answer. So moving into the technical challenge as posed by industry, proactive and predictive detection and management of asset integrity is in the ability to detect early failure precursors, defects, and their measurands. This is most often in enclosed or obscured targets, which leads to the requirement for the detection of surface and subsurface within target defects. These can be typified as fluid ingress, delamination, corrosion. So the frequency modulated continuous wave system provides visibility ultimately to the state of health and failure modes in porous media, which are often enclosed within protected dielectric materials such as paints and polymer coatings. So microwave sensing relies on the interaction of microwaves with matter, which ultimately means that target health information can be obtained by processing the reflection of the scattered, re-emitted, absorbed, or phase change of the electromagnetic wave that interacts with that object and then returns to the sensor. So microwave sensors display generally such advantages as online runtime monitoring, but due to low power requirements, low sensitivity to harsh environmental conditions. So in other words, the sensor can see through fog, mist, smoke, and low dielectric solids, which ultimately means we have a means for non-destructive tests and fast measurements. So the challenge with frequency modulated continuous wave sensing ultimately relates to understanding of the data and signal analysis and resultant algorithms developed to exploit both model and real world systems. So K-band analysis over a continuous sweep in frequency offers key advantages over higher power pulsed single frequency methods. So these methods are improved signal to noise characteristics due to the broader frequency range, a lower intermediate frequency, which is the difference between the output and received signals. Platform-mounted demonstrators of this system have verified that the capacity of this sensor to asset integrity measurements through dielectrics while targeting metallic materials and fluids. This is actually the subject of another presentation held at this event, which has got the serial number OTC 30840, and is about the self-certification and safety compliance, a framework for safe and secure operations beyond line of sight robotics in offshore infrastructure, which you can see the reference at the bottom of the screen here. But this research ultimately demonstrates the capacity to detect deformation and predict failure within a loaded geomaterial sample. So in other words, previously we have used the radar to detect static or very slowly occurring contrast in target properties, as is referred to in this other paper. What we do in this research is apply the contrast detection to a real-time situation with dynamic deformation. We find we cannot only observe the contrasts as they happen, but we can also observe the failure precursors which enable failure prediction. So we believe this to be the first for the application of any non-invasive, non-contactive sensing method with the potential for diverse and impactful applications for asset integrity monitoring. In particular, geomaterial and infrastructural load monitoring, so that can be for oil and gas applications, that can be for subsurface reservoir storage and seal integrity, that could be for mine integrity, nuclear storage, geothermal borehole stability, and building integrity. So to run through some of the applications that we have tested to date. So on the one hand, we've looked at porous media, internal and dynamic properties, in particular in sandstone and concrete. Those are the two upper pictures that you see there. We've also looked at asset integrity, where we've looked at corrosion on metals, which is the lower left image. We've looked at salt dispersion on road structures and potholes within that structure, which is the middle image. And we've also looked at renewable energy generation turbine blade defects. So in other words, we've been looking for areas of delamination, water ingress within the structure, which is not immediately apparent from the external view. And to focus in on the research that I'm presenting today, we're looking more at the porous internal media, dynamic properties, particularly of loaded sandstone. Now this obviously has applications toward loaded concrete and ultimately can fall under the asset integrity banner. Now I'm not going to go too much into the theory of the FMCW today, but the reference that I'm providing at the bottom of this slide certainly goes into a lot more of the theory. So you can, if you feel the inclination, can go and look at this this reference and have a bit more of an idea on the FMCW theory. So in experimental geomechanics, it's common practice to present your data as a stress-strain plot, which is ultimately telling you about the load versus time and deformation of your sample. So the left-hand graph here is explaining some of the stages in which deformation will go through within cemented sandstone. So as the principal stress or the vertical load on the sample increases, you get some axial shortening or strain of that sample, where it typically barrels out a little bit at the middle, but generally it's getting shorter. And then you start getting a grain crushing and pore collapse. This is represented by the shelf at point 1 on the left-hand graph. Now, once some of that pore crushing accommodation space has been taken up, then the sample is able to resist load again. So you start to see this increase in gradient until you get to the point where you've reached the end of the material's capability to resist that load, and you start to see wholesale fracture within that sample. So if I move on to the right-hand graph, this gives us a bit more of the evolution of that. So for point A, you've got small areas of decementation essentially happening. So the cementation between each grain is starting to fail, and in an unconfined sample, which we're talking about entirely throughout this presentation, you're generally getting vertically aligned fractures, which I think you can probably just about see in this left-hand 0.6 sigma max image. So as the load increases, obviously more of the cement grain breakage, and so you get more and more of these micro fractures occurring. As you get up towards between B and C, you're starting to see these micro fractures starting to join up, and you're getting up towards the maximum load capacity of the sample. And as you get past point C, a lot of these grain fractures have joined up, and you're really at this runaway point now where the sample is unable to resist any more load and whole fracture occurs. So in the previous slide, I discussed the grain-grain relationship and how deformation affects that. Well, the logical next step is to try to characterize the samples that have been loaded, and to do so, we've analyzed them using energy dispersive X-ray via scanning electron microscopy. So it gives us an ability to understand what is the compositional nature of the samples. And the EDX method allows us to understand what is the relative proportion of quartz versus clays and feldspars and the presence of other metals within that sample, which you can see in the bottom left of each of these images as the elemental makeup of each of these samples. Now, this is actually quite important in understanding how these rocks are going to respond when they are subjected to the FMCW or microwave analysis. Or in other words, how is their reflection going to look in terms of how conductive, metallic, the internal structure of this sample is. To continue with the sample characterization work, we understood that the distribution of high permittivity inclusions was going to vary from sample to sample. So a necessary step was to quantify that variation to inform on the reflected microwave signal in the upcoming tests. The left-hand images, top and bottom, the Darney Sandstone, show a fairly uniform distribution of high permittivity inclusions, metals such as iron, aluminium content in the clays and feldspars. The right-hand side images show the Red St sandstone, which exhibits concentrations of high permittivity inclusions and layering. So what we ascertained from this characterization work was that the Darney 2T sample with a volume content of the highest permittivities of 0.08%. So the highest content permittivities, as I say, are distributed metals. The Darney 2B sample, B stands for bottom, T stands for top, with a volume content of the highest permittivities of about 0.13%. The Red St B's top sample with a volume content of 0.21% metals. And the Red St B's 2B sample with a volume content of metals of approximately 0.19%. And finally, to round off the equipment characterization section, it's important to understand what does the footprint, essentially, of the radar signal look like. So we characterize this in an anechoic chamber, and we now understand what the radiative pattern resembles. So on the left-hand image, we're getting amplitude measurements, and on the right-hand image, we're looking at phase shifts. What we're getting out of both of these images is the dispersion characteristics of the emitted signal, which when we keep the radar antenna approximately 10 centimeters away from the sample, the red spot, for example, on the left-hand image is of the same dimensions of the sample itself. So that's telling us that the majority of that radar radiation is striking the target approximately the same dimension. Now, these are both two-dimensional images. Now, in the top left here, I've given you a brief 3D representation of what that dispersion characteristic looked like. So you've got your main lobe on the center line, and then you have these side lobes, which are of much lesser intensity. And we essentially disregard these from our radar returns. And now to give you an overview of the experimental setup itself. So what you see on the left-hand side are the sandstone cores as they were cut from the sandstone blocks. So that is a 38 millimeter diameter and a 76 millimeter sample length, which is a standard dimension in geomechanical work, experimentation. So you're also seeing sigma 1 being the axial load on the sample as applied, and sigma 3 equal to sigma 2, which is essentially saying that the radial confining pressure is equal and essentially zero. These were unconfined tests. So The middle image is showing you the heat shrink jacket that was applied to the sandstone samples, because when we load them, they're going to fracture, and we don't want them to lose their approximate coherence. We want to keep those samples together for later work and other characterization work as well. So okay, we put this into a hydraulic press, we applied load, and we caused them to fail while we're reading FMCW data. And to give you an idea of what that FMCW data looks like, I think it's necessary to go into a little bit about what the return signal is when you explain it. So generally, we're looking at frequency domain return FMCW transforms. Now, just to give you that overview, the x-axis on this graph is a distance measurement. So point 1, you see the main spike reflector. That's actually an artifact of where the microwave waveguide meets the antenna. So point 1 is a constant throughout all of the experimentation that we've been doing. The real data happens beyond point 2, well, between point 2 and point 3. So that's between bin 47 and bin 50. And remembering that these are distance measurements away from the antenna. So we're looking at between 46 and 47 is the end of the antenna to the target, which is about the 10 centimeters. Well, it's exactly 10 centimeters, actually, we measured it. And then you've got bin 47, which represents that first interface into the sample. And then bin 50 represents the exit interface into the sample. Now, the inset shows you the peak amplitudes for this data set. So anything before the peak is noise from the waveguide, and anything after the peak is noise from the shadow of the target. What's the most important part of this graph is actually occurring at bin 48. That is where all of the data that comes subsequently in this presentation is taken from. So in other words, bin 48 is the distance slightly inside the sample. And it's bin 48, which is where all the contrasts are coming from that are telling us what's happening inside the target. So now I'm going to talk you through the dynamic results for the Darney sandstone. Now the top left graph is talking about axial load. So this is the incremental increase in load on the sample as a function of time. And as you get to the peak of that graph, much like the graphs that we saw earlier on in the deformation theory section, as you start to get to the top of that peak, the sample has failed. So in other words, the maximum load for this sample occurred at 342 seconds. But if we look at the reflection coefficient as acquired from bin 48, as shown in the previous slide, we're seeing a decrease in the reflection coefficient that troughs some 22 seconds before the fail point. Or in other words, the reflection coefficient decreases until it gets to a turning point in advance of the failure. Now this is neatly reproduced in the second sample. You're seeing again the increase of the load to the fail point, and again in advance a turning point in the reflection coefficient. Now what's worth noting at this point is the 0.13 metallic content corresponds to a higher reflection coefficient than the 0.8 metallic content. 0.08 metallic content corresponds to a slightly lower reflection coefficient. So that's in keeping with the understanding that more metals within the sample will give you a higher reflection coefficient. So for the Red St sample, it's a very similar story to the Darney sandstone. We load to failure and we see a general decrease in the reflection coefficient to a trough point, which occurs well in advance of that fail. Now for the second Red St sandstone, we see a slightly different result. This is interpreted to be because there was a fracture or some slippage within the layering that has been observed within that sample. This is denoted by point 1, where we see this very brief relaxation in the load profile. And we're also not necessarily seeing a trough. In other words, from the moment this sample was starting to load, it was already starting to fail, which is in keeping with the idea that there was already a predetermined a fracture within that sample. So what these next two slides are going to show you are the general rates of change for the axial load and the reflection coefficients for those same samples that you've just seen. But what's important here is that I've taken the red line to denote failure on the right-hand side of all of these graphs, and that we're seeing changes in the rates of change for the axial load, which peak again in advance of the failure. Now, what's important again to notice is that for the change in reflection coefficient, everything's constant right up until you get this runaway change in the reflection coefficient, which is consistently in advance of the failure point. So again, in keeping with the previous slides, we're seeing very much the same story for the Red St sandstone. We're seeing an increase in the rate of change. We're seeing a peak in the axial load that's in advance of the runaway spike for the reflection coefficient. Now, the only departure is for the second Red St sandstone, which shows you there's this sudden dip in the ability to resist load, which is again is in keeping with that fracture event that we observed in the previous slides. So, with all the results collated and tabulated, we can see that there is a consistent trend that gives us a reflection coefficient spike time that occurs well in advance of the actual sample failure, which ranges between 12 seconds for the Darney top sample and 35 seconds for the Red St bottom sample. So that seems to be a fairly consistent range. So let's walk through a summary of these observations. The minimum reflection coefficient, the turning point in that reflection coefficient for all samples with a negative gradient becomes positive, coincides with the maximum rate of change in the applied axial load. So in other words, that's the peak of that change in axial load graph. Secondly, the rate of change in the observed reflection coefficient, the changing gamma peak, coincides approximately with the runaway formation of microcracks, and that's in keeping with the theories put forth by Jaeger et al. 2007 and Isner-Rudnicki in 2000. So, thirdly, the rate of change in the observed reflection coefficient becomes a high value, or in other words, where the rate of change of gamma has a turning point, represents that irrecoverable deformation and could be used to indicate imminent failure of a sample when it's under experimental loading conditions. So, and certainly for the Darney samples, that minimum in reflection coefficient seems to correlate with that turning point. So overall, these results represent the potential for a significant advancement in non-contact, non-invasive detection of faults and fracture formation within a loaded geomaterial or concrete, and may offer insights into previously unavailable data that was to the experimental geomechanicist. So to move on to a discussion of these results, we've made assumptions that axial compression results in pore volume contraction throughout the loaded sample. We've also assumed that the number of nominally open interfaces within a bulk field of view within that geomaterial sample also reduces upon loading. So this model would explain the initial decrease in the observed reflection coefficients as each sample is loaded, with the notable exception of the Red St sample 2T, which was already fractured and started to fail the moment we loaded it. So there's a sharp increase in the reflection coefficient due to granular failure and breakage of these cementation between the grains. This demonstrates the role that microfractures play prior to their amalgamation into the larger scale macrofracture, which overall leads to the sample failure. Therefore, we're taking that the presence of microfractures may equate to a marked increase in planar interfaces, which in an unconfined sample are generally expected to be oriented vertically throughout the sample, as previously explained. So vertically oriented microfractures represent an increased reflectance from microwave energy propagating at normal incidence to the axial alignment of these microfractures, so resulting in an increase in the observed reflection coefficient. These results show that a consistent and detectable change in the reflection coefficient as a function of applied load in advance of sample deformation yield and failure can be observed. So I'll round off with what we've concluded then. An increase in observed reflection coefficient in a loaded sample due to an increase in microfracture events. We can see that. The amalgamation of microfractures into a macrofracture may be observed and monitored in real time, and crucially, prior to the failure of the loaded sample. It now has a predictive capability. So the radar offers the geomechanicist with a new level, potentially, of experimental control for post-yield and pre-failure study and detailed characterization of the evolution in reservoir rock failure mechanisms. And if this is proven to be consistent through further experimentation, this application of microwave sensing may result in a deployable sensing modality and may also offer significant improvements in reservoir modeling for all subsurface industrial applications. So thank you for watching, and it's been a pleasure to share my research with you. And I am the corresponding author, so here are my details. If you have any questions, I'll be more than happy to communicate and engage. And enjoy the rest of the virtual conference, and stay safe and well. Thank you.